So I'm a professor of computer science at a polytechnic. So we're an institution with about 3,000 students, and we offer various sorts of engineering majors. I used to be an ML engineer in industry, and so this talk kind of comes out of that. As we know, machine learning is used for all sorts of real-time prediction, right? So we have APIs where requests get sent and we want to make predictions. You know, today when I used my app for Uber, I had it telling me, okay, this is how long we estimate until we connect you with the driver. This is how long the distance is to where you're going and how long it'll take given current traffic conditions, you know, things like that. So we are incorporating machine learning into everything and all sorts of endpoints. But there's a small challenge. When we get a request to an endpoint, like a REST request like this, it's going to contain a record of data, right? So in this case, we want to predict the home price, the sale price. But machine learning is about approximating a mathematical function. So this function takes in a vector of numbers, but that's not what our records look like, right? In fact, we want to convert our record into this vector of numbers, so this is feature extraction. Now, there's all sorts of aspects of this. Some of it is simple as one-hot encoding categorical variables, right? So that we can easily draw planes, right, to separate out different values. Calculated features, such as, you know, body mass index is calculated from your weight and your height, for example, that allow us to get more predictive power than the raw input data. We might cluster data. If we had geographical data, we might cluster it, right? Dates and times. So machine learning models are generally speaking pretty bad at inferring periodicity. So we need to extract the sort of different periods of the day so that the model can learn, okay, in the mornings, my traffic level is going to be higher than in the midnight, you know, at midnight. Similarly, when dealing with periodic signals, if you just sort of represent them as a single value, there's this sharp break when they loop back around that machine learning models can't handle. So you may want to project it into a two-dimensional space. If you have a bunch of like complex records, so say a bunch of clickstream data for users, right? You looked at what products they looked at, or you have medical records. You have an arbitrary number of records, you want to collapse those down into a finite number of features, so a fixed number of features actually. And so you may compute various statistics on either the signal, or you may do various sort of summary statistics, things like that, to use those as features. Another example here is we have multiple algorithm models used for classifying email as spam or not. So we have logistic regression, random forests, multi-layer perceptrons, and naive Bayes. And we see that using not just the body of the email, but the domain of the sender and the user agent information increases the accuracy, right? So there's a lot of cases where we want to bring in complementary data. We don't just want to take the record we're given, we want to pull other data sets in that allow us to make more accurate predictions. One example of useful data, the American Community Survey, right? So if you happen to have zip codes in your data set, then you can grab the median household income, the population size, age ranges, household sizes, poverty levels, the fraction of people who own or rent their home, educational attainment, things like that. That can be incredibly rich data, right, that can help improve the accuracy of your models. You may be working with a problem that changes with the weather, right? So there's a data set out there, the bike demand data set from the Capital Bike Share program. And if you look at their data, you see, oh, look, when the weather's bad, there's far fewer people renting bikes, right, to commute to work. So you might want to incorporate the most recent, you know, current weather data. There's startups out there and companies working on precision agriculture, right, where they're basically trying to monitor the growth of plants and help predict when you should sort of put on fertilizer and water and things like that to try to maximize your yield. And so they might incorporate all sorts of geospatial information and satellite images and things like that. In addition to basically taking all of that and bringing in all that data and transforming it all into these numerical vectors, we also have to handle missing or outlier data, right? So on the left, I have a distribution of square footages of homes, and with a bunch of them having a value of 0. So whoever was entering those records didn't know the square footage, so they just put in 0. So we need to replace that with a more reasonable value. So that's imputation. So this is part of the data cleaning process. And it turns out if we don't do a good job of data cleaning, it can be very costly. I mean, this is an extreme example, but does anybody remember when the Mars Climate Orbiter crashed? It didn't land, right? This is because one of the contractors was using imperial units and NASA was using scientific units, and their software just modeled numbers, not the units, right? So they ended up using different units. The software was incompatible with the hardware, and it crashed because they couldn't control the entry trajectory correctly. So once we've done all that, we have this nice numerical vector, right? And we can apply our model. Now the question is, do we do all this ahead of time? Right? So do we do offline feature calculations? There's advantages and disadvantages to this, right? So if I'm doing offline feature calculations, I probably have some sort of batch job that runs periodically to recompute all the features for my records or objects that are coming in. And I have some sort of key value store I'm using to retrieve those values at prediction time, right? Now, this works if you know all of your objects ahead of time, right? So if it's, say, a database of real estate and you know every house that's on the market, that's fine. But what if you want users to be able to input things that you've never seen before, right? They just give you an address for a property that you maybe have never seen. Well, that doesn't work so well if you're relying on all the feature calculations being done in the background and just doing lookup in real time. It's also expensive, right? These pipelines take a long time to run, and you may be computing features for objects that you very rarely see at prediction time. So it's not really worth doing all that computational work. And with the cost of cloud, right? The other aspect of this is sort of delayed response to changing environments. Okay, so what happens when, if you think of ad targeting, for example, I happen to be a fan of math books. And so what happens when I go and visit a publisher's website? Very shortly after that, I see ads for books from that company. So they're responding very quickly to my browsing habits in near real time. And so depending on where you how you design your architecture, if you're putting a lot of the feature engineering or feature extraction in a sort of a back-end offline system, it may take longer to have that updated data available at prediction time. So what I teach my students is to implement their services using a pipeline like this, right? So we have a RESTful service or something similar, and we get a request. And the first thing we're going to do is we're going to pull in enrichment data. So this is that American Community Survey data, right? If we have a zip code, or ways of identifying things that are located nearby geospatially using latitude and longitude. So we have all this enrichment data that we pull in and we augment the record with. Then we clean the data to remove outliers or handle invalid values. And then we go through the feature extraction stage to produce a vector of numbers. At that point, we can pass into the model and get a prediction that we can pass back to the user, right? So this is basically the architecture of what an online prediction pipeline looks like. okay? So how am I going to go about implementing this? On the one hand, I'm definitely going to need some key value stores to pull the enrichment data from. I'm going to need some pipelines to keep those enrichment stores up to date. So ideally, the data I'm storing in the enrichment store are things like information coded by zip code that are not unique to a given object. So it's a much smaller set of data than if I had everything already joined with all of my objects. Then, we need to calculate, we either implement all of this in a single RESTful service, or maybe we're not doing it synchronously like that. We have an asynchronous format, so we can use a message broker, right? So we can run separate services and pass them through a message broker, and we can use streaming pipelines for this, right? So Memphis, who's sponsoring our talk today, is developing a event streaming and processing platform. So the idea is that it has durable queues and pub sub systems, right? Like a traditional message broker, but it's durable like Kafka or Pulsar. The main difference is that it's designed to be low overhead, very cloud friendly, and designed for ease of operation and use. So it's supposed to be, instead of just, it does technically what the other products do, but it's designed to be much easier to manage and operate and use. On the other hand, we also have Bytewax, which is a streaming pipeline framework, right? So think of it as an alternative to Apache Spark. The main difference is that for me, when I'm teaching my class ML production systems, it takes me about 6 lectures to get folks to a point where they can be comfortable using Spark. It takes me 1 lecture with Bytewax, right? So they're much easier to use. It's all in Python. They can just do a pip install, whatever, right? So I use Memphis to hold my records waiting to be processed. And then I use Bytewax to implement a stage of the pipeline, process some data, and then move it into the next queue. Bytewax has what you expect, sort of standard stateless transformations, like a filter or a map. But it also has a really rich library of stateful transformations. So one example is a stateful map. Let's say that you have clickstream data. So you have every time the user views a product, you get a message for that. And maybe you're calculating features off of that, right? You want to look at how many products are they looking at. Maybe that's an indication of they're searching for something but not finding what they want. Or how many times do they look at each product? Maybe if they keep going back every few days and looking at a product like a laptop, that's an indication of intent to buy it, right? And so we can use these stateful transformations to basically keep track of the state for each object, and as we receive new messages, update that state. So we don't have to recompute it from scratch every time. And then when we do, we can emit those updated states as messages and maybe store them in, say, our enrichment store or something so they can be pulled later. So there's this, the more you can move to the online prediction pipeline is fantastic. But you may not be able to move everything there. And so having the ability to do incremental computation is a huge benefit for these architectures because it avoids having to implement batch pipelines that reprocess all the data every time, okay? Now, when you combine Memphis with Bytewax, you get this very cool opportunity to see into your system. So Memphis has this overview where it tracks each application that's connected to one of its, what it calls a station. And so you get a view of your entire system with these purple boxes being stations, the yellow boxes being producers, and the green boxes being consumers. So it allows you to actually see overall, holistically, your system. How many different pipelines are you running, and what are their states? I don't know about you, but when I was working in industry, I think one of the hardest problems was that all the frameworks I used were designed to basically sort of treat each pipeline as a separate entity, separate deployable entity. And it was easy to get lost when you had 20, 30 different pipelines running in production, right? That's a lot to keep track of and manage. So having a platform that provides the ability to actually see your system at a glance and see all the components and their interconnections is a huge step up, right? So, yeah. I'm going to pause here for a second. Are there any questions before I continue? Sorry, can you give them the...
How does Bytewax handle faults with the stateful map? Recovering from a failure on the stateful map.
Okay, so Bytewax actually, each worker will incrementally write out data to a SQLite file on the local node, and then the current practice is to back up those SQLite files periodically to S3. So I agree. If you have state running in the pipeline, right, you want to be able to recover. So you can control how often that writing of state occurs. And if you develop your own operators, you basically provide functions that enable you to initialize the state and to update the state. And so it stores that so that it can recover the state in the future. How many of you have used online feature extraction? Or like, how many of you, by show of hands, have worked on, say, production ML systems, some sort of endpoint that's using a model? Okay. Did you use online feature calculations, or did you mostly do offline? Online? What were some of the challenges that you faced in doing that? Yeah, so what I'm really excited about these technologies and where this kind of was a big sort of mind-blowing aspect for me is when I was working in industry, we were using batch pipelines for this because we had hundreds of millions of different objects that we were doing prediction on. And actually most of our team's time was spent on sort of dealing with failures in that batch process. It was very complicated, very heavy, difficult to recover from. And so being able to do more of this online really makes it much easier to handle those faults. And because it's done sort of later in time, and you only need to do the updates for things that come in. And related to that is, like, one of the patterns I found really useful was using the queues in Memphis as a sort of way to handle incremental computation. Right? So I could actually write out state to a queue and then pull that state later, update it with new information, and write it back. So I could use Memphis, or similarly Kafka or Pulsar, as a database rather than just a temporary place to put messages so that another process or another service could read them. I found that to be a useful approach for kind of handling the state outside of the computational framework, right, from a storage perspective, which also has its ups and downs with respect to recoverability and lookup time. So, all right, any questions? All right, well, thank you, folks. I appreciate your time. Hope you learned something, and have a good day.